Good day. Today I shall defy the laws of physics and give you the fastest lesson you've ever seen, practically faster than the speed of light. So today we're going to talk about Dalton's law, unit 2.8. So we know that gases exert a pressure, right? Depending on the number of collisions that occur, the higher the number of collisions, the higher the pressure. Now that depends on many different things like temperature and number of moles. So in this case, we're going to be comparing pressure and number of moles. So Dalton says that the more gas we have, the more moles of gas we have, the more particles there are, the more collisions there will be, and of course, the higher the pressure. Now, if we combine different gases together, we're basically multiplying the amount of particles and therefore multiplying the number of collisions and thus multiplying the amount of pressure that is exerted. For example, if I have a gas, I have 5 moles of gas. So that 5 mole of gas will exert 100 kilopascal based on the amount of collisions that it creates. I have another gas, gas B, 25 mole of it. Now, because I have more mole of gas, I'll have more collisions and therefore I'll have a greater pressure in this container. If I combine those two gases, I end up with how many moles? Of course, 30 moles. 30 moles is much more gas, so there should be more collisions, and therefore the pressure should be greater, and indeed, it's 600 kilopascal. Now, there is a direct correlation between gas A, gas B, and the mixture. If gas A represents a sixth of the total amount of moles, well, its pressure should represent a sixth of the total pressure as well, right? And it makes sense. Same thing here. If I have 25 moles out of 30, well, that's a fifth, sixth of the number of moles. The pressure of this gas should represent also fifth, sixth of the total pressure. So 500 over 600, or 500 out of 600 kilopascal. Okay, so there is a direct correlation. So Dalton said, therefore, our total pressure should be a combination of the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 and so on and so forth. The same way, there should be a relationship between the number of moles, which we have here. So since, as I showed you, that there is a relationship between 5 out of 30 and 100 out of 600, we can take those ratios and come up with this law. So the pressure, what we call the partial pressure of gas A versus the total pressure of the mixture, this should have the same proportion as the partial number of moles of gas A versus the total number of moles of gas in the container. So this ratio is equal to this ratio. So that's Dalton's law, right? At a given temperature, the total pressure of a mixture of gases equals the sum of pressure of each of the gases. Now let's look at a mathematical example. So we have here, at a given temperature, a mixture of gas contains 3.35 mole of neon, 0.64 mole of argon, 2.19 mole of xenon. What is the partial pressure of xenon if the total pressure of the mixture is 200 kilopascal? So first thing we need to do is write down our information, or some of it anyways. So let's pick a color. Let's go with blue as usual. Okay, so we said that the equation is partial pressure of gas A, which is xenon, versus total pressure of the mixture is equal to the number of moles of gas of xenon over the total number of moles of gas. Okay, now what do I have? I have the number of moles of xenon, and I have the total pressure, and I have the different amounts of moles. So first I will calculate my N total. So my N total is 3.35 plus, so that's for neon, 0.64 for argon, plus 2.19 for xenon. That gives me a total number of moles of 6.18. So I found this value. The total pressure is given to me at 200. I know the number of moles of xenon. I can now calculate the partial pressure of xenon. So if I replace, I will have partial pressure of xenon, oops, like this, over the total pressure, which is 200.0, is equal to the number of moles of xenon, 2.19 mole, over the total amount of moles of gas in the container. So now I can solve for the partial pressure of xenon. And that is equal to, if we look under the box, 70.9 kilopascal. There you go. That was your lesson on Dalton's law. Bye.